Hello, this week we are going to be talking about carbon, biogeochemical cycles, clouds, and aerosols. So we've got a lot to talk about. Let's dive right into it. I will share my screen and start the PowerPoint. Here we go. Okay, so carbon, first we're going to talk about carbon and other biogeochemical cycles, focusing mainly on carbon. So the global carbon cycle is demonstrated in this image. And just like other cycles that we might be more familiar with, like the water cycle, we know that these substances are exchanged from reservoir to reservoir to reservoir as they move through our system, right? So it might start in the ocean, move into the sediment, be consumed by organisms, go back into the soil, be burned up into the atmosphere, and so on and so on and so on as it moves around our Earth. So there's these series of reservoirs. Each of them are connected by exchange fluxes. And the reservoirs hold the carbon for varying amounts of time, right? Sometimes the carbon is kept for only a short period of time, such as if it gets stuck in grass that's, repeatedly mowed in somebody's yard, or it could be stuck for a long period of time if it goes into perhaps a rock that sticks around for hundreds of thousands to millions of years. So thinking about the processes and the reservoirs and their time scale, land uptake, when we think about plants, photosynthesis, respiration, animals, those occur over time scales of, a year, maybe up to 100 years or so. When we think about the ocean, that's going to take a little bit longer, maybe up to 1,000 years or thousands of years. Reaction with rocks, such as calcium carbonate or silicates, and that's going to be even longer. That's going to be thousands to hundreds of thousands. So coming back to this, you'll notice that there's a lot going on, right? So let's break it down. So what do the numbers in the boxes represent? Well, each of these boxes are the reservoirs, right? The vegetation, the ocean floor, the surface ocean, the marine biota, all of those are reservoirs. And the numbers represent how much carbon is currently there, right? How much is currently in that reservoir. So what are the numbers next to the arrows represent, right? What are these arrows? Well, those are the exchange fluxes. That is the rate of exchange, how much carbon is currently moving between these reservoirs, right? So how much is moving from the atmosphere to the ocean? What is that rate? And then finally, what is indicated by the red text? Well, the black text is natural, right? So that's natural volcanism, natural rock weathering, natural oxygen atmosphere gas exchange. That would happen regardless of humans. The red is everything that humans have introduced. And notice that the red arrows go both up and down, right? So we as humans cause carbon to be released into our atmosphere, but we also cause carbon to be taken down from our atmosphere. So we're doing a little bit of both. As you know, hopefully, that's not imbalance. We are actually causing a net export of carbon into the atmosphere, disrupting this natural system. Right? So since the beginning of the industrial era, humans have been producing energy by burning fossil fuels like coal, oil, and natural gas. And this process releases huge amounts of carbon dioxide into our atmosphere. The total cumulative emissions between 1750, so around the start of the Industrial Revolution, to 2011, so a little while ago, but fairly recent when we still have the data, it's about 375 petagrams of carbon, right? That's huge. And that's including a contribution of 8 petagrams of carbon from the production of cement. We don't often think of cement when we think about climate change, but that actually is a big cause of global warming, because when we produce cement, when we build buildings, when we pave parking lots, build roads, all of that good stuff, we are releasing carbon. Okay. Second major source of anthropogenic carbon emissions to the atmosphere is caused by changes in land use. So in order to build these buildings, in order to build these roads, we have to, cut down forests. In order to have all of the food we need to cut down forests and build cropland, right? So it's mainly deforestation. And this is going to cause that net reduction in the amount of carbon that vegetation reservoir can hold. Right? So what percentage of ice-free land, meaning land that like humans could reasonably occupy, has been converted from forest to cropland or pasture land since 1750, do you think? So since the Industrial Revolution, how much of our land that we can alter have we already altered? The answer to that, it surprised me, it's about 40%. 50 million square kilometers. So this image is showing the global distribution of cropland and pastures in the year 2000, and the intensity of color represents the percentage of area that has been altered. And so you can see that, right, pretty much everywhere that humans live, meaning not, deserts, not incredibly dense rainforest, we have converted to cropland to sustain ourselves. So you have to wonder, is this sustainable, right? Can we keep going at this rate? If in just 200 years, we've converted 40% of our land to cropland, can we keep doing that? Well, no, because we're eventually going to run out of land to convert. So instead of converting more land, looking towards the future, we just need to get more efficient with the land that we've already converted, because this rate of land conversion, not only is it bad for global warming, obviously, it's just not sustainable. We will eventually run out of land.